a sequence is an ordered list of numbers, and the series is the sum of those numbers in the sequence. And so never lose sight of this as things get harder, right? So you got to have this in place. If we're talking about a sequence, you're immediately thinking this is a list of numbers in an order. And then the series of that sequence is just where we're going to add them all up. So the sequence, series, and then we talked about the sequence of partial sums. So the sequence, here's a particular sequence. The series then would be just to add those all up, right? So our conception of it is kind of the way a second grader would conceive of this. Just take the first one, add the next one, add the next one, just keep adding up and just add up all the terms. And then we have a shorthand notation for that in calculus. This is sigma, which means sum up. Sum up a bunch of things that look like this, right? So this is our ith term of the sequence. And then this tells us we're going to let I be every number starting from 1 to infinity and get all those terms and then add them all up. Sequence of partial sums. So we can make a new sequence out of the series by taking the first partial sum, which is the first term. And then the second partial sum is adding the first two terms. And then the third partial sum is adding the first three terms. The fourth partial sum, add the first four together. And this makes a new sequence based on that series, etc.
Are you recording?
I am recording, thank you. Okay, so remember that. Any questions on that, just that overview there? Okay, so let's take a look at, in your homework, you're going to have some problems where they're going to have you download no, we're not ready for that yet. Let's see. We're going to do let's do an example here. Yeah, here we go. So let's do this example as a good review, and it gives a real-world context to this stuff. So a turtle is walking across your back lawn, and on day 1, he started at the east end and walked halfway across. And then on day 2, he walked half of the distance remaining to get to the west end. In other words, he walked 1/4 of the total length of the lawn. And then every day he continued this way, always walking half the distance remaining to get to the west end of the lawn. Okay, so we're going to write a sequence of the distances walked by the turtle each day starting from day 1. And we're going to do it as a list. Just list them out, and then we're going to figure out the formula, the general term for the ith day. So let's make the list. Here we go. So remember, we're gonna put the list in like chevrons, and then in chevrons. And so I think in iMath AS you're going to use less than or greater than. If they're asking you actually to put them in chevrons, you use the less than sign, the greater than sign. Okay, so what was the first distance? On the first day, the turtle walked how far? What did we say?
1/2.
1/2. And on the second day, how far did the turtle walk?
1/4.
1/4. And then every day walking half as much as he did the day before, or half the distance left to the west end. So then be 1/8, 1/16, 1/32, etc. Okay, so we want to write a formula for this. So clearly, the numerator is always 1. So we just got to figure out what the denominator is. So this is I equals 1, I equals 2, I equals 3. It's always really helpful when you're trying to determine these formulas. Make kind of a table. Write down the I values so that you can compare them. So 1 gives 2, 2 gives 4, 3 gives 8, 4 gives 16, 5 gives 32. So how do we do that? So this is I.
Is it 2 to the I?
She wants 2 to the I. So 2 to the 5th, that's 32. 2 to the 4th, that's 16. 2 cubed, looks like she's onto something there. Everyone agree? Okay, so now let's express the series associated with the sequence, right? So this is the sequence of how far the turtle walks each day. And now we want the series. So what do we say the series is? So let's write it like a second grader would write it. How do I write the series like a second grader would write it?
Did you say that it's you or
Somebody?
Sorry, did somebody answer already?
No, go ahead.
Okay. We would just, the series is basically the sum of all the numbers
Yeah,
in the list.
yeah.
So half plus 1/4
Yeah,
plus 1/8 plus 1/16 and
That's
so
it.
on.
that's it. You just add them up, right? That's the series. Add them up. But this is an infinite. It's an infinite series, so we have dot dot dot. Let me just continue on this way. Okay, now let's write it like we would write it in calculus. So we know it's a sum. I starts at 1, goes on forever. And then what are the terms that we are adding up? So what do I put here to get that sum of numbers?
Will it just be 1 over 2i?
Yeah, 2 to the
power
I.
of I.
Yeah, that's it. So it's the same as this. It's the same terms as the sequence, right? Because that's what it is. It's the sum of the series of the sum of the terms in the sequence. So we take the general ith term of the sequence, and we let I be 1, and then 2, and then 3, and then 4, and add them all up. Okay, questions on B? Okay, so now we're going to do the sequence of partial sums, right? So now we got this series, and we're going to write some partial sums here. So let's start over here. First partial sum is 1/2. Second partial sum is 1/2 plus 1/4. Can we just skip right to 3/4 for that? And then the third partial sum is 1/2 plus 1/4 plus 1/8. And what is that? 7/8, right? Everyone's here, I'm getting these numbers. Fourth partial sum, 1/2 plus 1/4 plus 1/8 plus 1/16. That'd be 15/16. Let's do one more. Adding the first 5 terms together, that's the fifth partial sum, and that's going to be 31/32. Are you with me?
Yes, sir.
Okay, so let's make a general rule for that one. Let's start with the denominator. So again, this is I equals 1, 2, 3, 4, 5. So 1 gives 2, 2 gives 4, 3 gives 8, 4 gives 16. Well, this is what we saw before, right? This is just 2 to the I. It's the same denominator that I had in the original sequence, 2 to the I. Now what about the numerator? So what do you notice about the numerator each time?
It's 2 to the I minus 1.
It's just 1 less than the denominator, right? It's always just 1 less than the denominator. So we can do that. We can say 2 to the I, and then minus 1. So we can leave it that way. That's fine. Or we could, if we have a sum of or difference of terms in the numerator, we could split it up. So we could do 1 minus, so 2 to the I over 2 to the I minus 1 over 2 to the I. That's another acceptable way to write this, either way. Oh, so that was what we did here. So the general term of the sequence, that's this. Okay, so what about the sequence of partial sums? We know this was how much the turtle has walks on each individual day. What about in the context of the turtle? What does the sequence of partial sums represent?
The total distance he's walked since the beginning.
Right. And what does that, is that familiar at all, that idea? So this is the total distance walked so far.
Accumulation.
Yeah, this is like an accumulation of distance, right? So we keep, the sequence of partial sum is like keeping a running total. It's like a running total of the amount that he's walked. And so that we know that's accumulation, right?
Is there any way for us to know when the turtle? Oh, that's the next question.
Mm-hmm. So this is accumulation of distance. So the only difference is before our accumulation was like a function, usually with a real variable, right? A continuous variable. So it's the same thing, but it's just a discrete list. But it still has the concept or the flavor of accumulation, right? It's like accumulation function. On the third day, the accumulated distance walked by the turtle is 7/8. On the fifth day, the accumulated distance walked is 31/32. All right, so the question, will the turtle ever make it across the lawn? Yes or no?
No.
Okay, I have a vote for no. All right, so we're actually going to, in a couple class periods, we're going to get to math to show whether he makes it or not. So we're just going to put that, I'll leave you in suspense. We're going to put that question on hold. Okay? So we have one vote for no, and so stay tuned. Okay, any questions on this example? So nice example of a sequence, right? The sequence means how much far the turtle walked each day. The series, adding up all of them. The sequence of partial sums, which is like an accumulation function, right? Accumulation of distance on the ith day. All right, so nice example. Any questions? Okay, so now we'll talk about GC. So in your homework, you'll often, there's several problems where you'll be asked to download a file and use GC to help us generate some sequences and series. So I'm going to show you how that works. Okay, so here's the type of file that you might see, and so I've got this one set up for our turtle example. So let me just take this. All right, so the table will already be there for you, and so K is what we've been using for I, but this says K, and so we said what was the sequence of distances walked each day by the turtle is 1/2 to the I, so it'll be 1/2 to the K. And notice that as soon as, if this header here is S of K, as soon as I get that function defined correctly for the sequence, the kth term of the sequence, it just gives it to us. If I can make this any bigger. No, that's not what I want. Well, I guess the table is stuck at that size. I hope you can see that. But okay, and so now we want to do the sequence of partial sums. So we got to think about how we can tell GC to do this, because we're not going to type out the list. We need to mathematically tell GC how to do the sequence of partial sums. So that will be capital S of K. And so how will we express the kth partial sum? So we got to think about this. So the kth partial sum is adding together the first K terms. So first of all, what will we use to do that? To express a sum.
A net accumulation function like an integral.
Yeah, but integral is like for a continuous variable. So what do we have? You know, like continuous variable, like every single value, you know, starting from A to X. So what do we have instead with this kind of discrete situation?
Are we going to have that symbol that, I'm sorry, I can't remember that. But
Summation.
Summation,
Yeah.
right? So Control-Shift-S gives you a summation. Okay? And so if it's the kth partial sum, how many terms, so this is like the last term here. How many terms will we have? If it's the kth partial sum, how many things will we be adding together?
10?
If it's the kth partial sum.
K terms.
What's that?
K terms.
K. So we want this number up here at the top to be K, right? Because we're going to add together K things to get the kth partial sum. That should make sense. So down here, do I want k to be my index? So for the kth partial sum, k stands for the total number of terms that I'm adding together. And when I do that, I need to cycle through every term. So what do I need down here? Do I want to put k?
Are we going to put S of k?
No. It's kind of like when we were doing an integral, right? And if we were integrating out to x,
Could we put like I or something?
yeah, we need something else, right? We just need something else. Just like in our integral, we use t often, like lowercase t and the rate function and dt, because so the kth partial sum, k stands for how many total terms we have. Not we need a different symbol to cycle through those terms. So someone said I, so let's use I. Sure. Actually, we get I is square root of -1, so use j. Okay.
Wait, what is the bottom telling us?
So this is going to be where we start. This is the starting value up to. So it's like how many things we're going to add together. So what are we going to start at? We start at 0.
Oh, okay. So, all right, I got it.
Do we want to start at 0?
That's right.
No, don't we start at 1?
We start at 1, right? So j is going to be 1, and that'll be the first term. Then j is going to be 2, and that'll get us the second term. And then 3, and then all the way up to k. And then we want to add all those together. So what am I going to put here?
S of k, which is like the 1 over 2k.
Okay, do I want to put s of k?
No, S of like another variable, or S of j.
J, right? J is the one that's going to cycle through all the values starting from 1 up to k. So yeah, I can do s of j, or I can do 1 over 2 to the j. It doesn't matter. So let's do s of j. And that's our 1 over 2 to the j. So j will be 1, and we'll get the first term. J will be 2, and we'll get the second term. J will be 3, and we'll get the third term, all the way up to the kth term, and then add those all together. That's the kth partial sum. So this should make sense. All right, so I'm going to select the table. So select the table so there's a blue border around it. You just click somewhere in there, and then you're going to go up to table, and we're going to add a formula. So we're going to add a formula, and it's going to make a new column, and we want that to be s of k. So I'll do capital, oops, what happened? So capital S of k, and lo and behold, look what we got. 1/2, 3/4, 7/8, 15/16, 31/32, etc. So there's our sequence of partial sums. Okay, and then just to check that, we know that's right, but we could check it with our, what did we get for, and I'll call this, say, f. What did we get when we did the general, we had that sequence of partial sums, and we figured out that its general formula was what? What did we find it was?
2i minus 1 over 2i.
Yeah, right. So so this is, in this case, it's k. So 2 to the k minus 1 all over 2 to the k. So here's a new sequence, and this sequence we said was the same as the sequence of partial sums. So if I can go to the table here, select it, and then go formula, add formula. And then right there I can do f of k, and what do I expect to see?
The same thing.
The exact same thing, right? It's got the same thing now as a formula and as actually literally creating the partial sums, but it's the same sequence. So that you'll be doing a lot of that in your homework, and this is all on video. So if you ever forget what to do, just you can go back to the video and watch this and remind yourself. So we want to definitely be understanding what's going on with these sequences and series, and the meaning and the concept, but then we want to use technology too. So technology is great to like generate these lists, these sequences super fast for us, so we can take more time to work on understanding it. So we want both, right? We want to use technology appropriately, but we want to we want to understand what's going on for sure. Okay, questions on GC?
So I have two questions. One is, when we did S of j, is that because we're referring to the initial function we made, which is half?
Yeah, I mean, what do our partial sums consist of? What are we adding up?
Well, each like ith or kth term.
Yeah, we're going to add up the terms of this one, right? So we're
Right.
making the sequence of partial sums. We want to add up, say, the first k terms of this. So I'm just using function notation to represent that sequence.
I see. And also, is S of k in a way an open form and f of k kind of closed form or so?
No, this is, let's see. I'm not sure about that. No, I think this is still a closed form. I have to think about that.
I see. So that's closed form, but then S of k is open because it has the summation.
No, I
in it?
think these are all closed forms. I can get back to you.
Okay, that was just a.
I mean, the
that
only
was-
one that might be open form is this, but
I see.
I don't think a sum. I don't think a summation is. Yeah, maybe it is. I don't know. I'm not sure.
Thank you.
But for sure, these two are closed, right? Because they easily generate lots of results really fast.
Yeah.
Okay, other questions? All right, so I'm going to take a look at, not that one. Where am I? There we go. Here's another example. And I want to write this series using summation notation. And in order to write summation notation, what I need the formula for the general term. Okay, so let's take a look. I got I'm gonna write this way. So I is 1, 2, 3, 4, 5, 6, 7. Okay, and then my ith term is 3, 11. Yeah, and I wouldn't even be able to predict what the seventh is here off the top of my head. So let's take a look at this. 1 gives 3, 2 gives 11, 3 gives 31, 4 gives 69, 5 gives 131, 6 gives 223. So let's call this just A. So harder, right? So it's like this is not immediately apparent what a formula might be to get us the ith term from I. So I'm going to show you something, a technique that sometimes is really helpful with these. What I'm going to do is I'm going to take the difference between 11 and 3, which is 8, and then the difference between 11 and 31, which is 20, and continue that way. So what is this? It's at 38. This is 62. And then what is this? 90 something? 92? Is that right? Okay, so what did I just do? I looked at how much this went up. What? For an increase of I of what? How much did I go up when this one went up by 8?
1.
1, right? And then the ith term went up 20 when I went up by 1. So each of these represents how much our term changed or varied when I varied by 1. So what kind of numbers are these?
Rate of change.
Rate of change, right? Rate of change is how much something varies per 1 unit change of your independent. So these are rates of change. And so if I do it again, let's do it again. This goes up 12. This goes up 18. This goes up 24. This goes up 30. So this now is the rate of change of the rate of change. And what do you notice about the rate of change of the rate of change?
Goes up by 6.
Goes up by 6 every time. So this is like kind of like what kind of function?
A linear function.
Yeah, so this is like a linear function, like a degree 1. And since this was the rate of change of this one, what kind of function might this be?
Quadratic.
Yeah, so this is quadratic, degree 2. And therefore our original sequence there?
Cubic.
Cubic. So this can be very helpful because I could write out now knowing, oh, hey, this is cubic, so it would relate to I cubed. So let's write out what I cubed is. 1, 8, 27, 64, 125, 216. And now maybe we can see a pattern between I cubed and our sequence. So 1 gives 3, 8 gives 11, 27 gives 31. Now there's something appearing here. Can anyone see it? This is
After I cube, they always starts adding by 2, but then it increases by 3, 4, 5, and so on.
yeah, do you see this is
It's I cubed plus I plus.
all right, so some people are seeing it. So add 2, add 3, add 4, add 5. And so this amount that we're adding, how does it compare to I?
Always one higher than I.
1 higher than I. So we have I cubed plus 1 more than I gives us the sequence. So that's it. I cubed plus 1 more than I. And so and then we can write that as a series. So that we can write that thing as maybe okay. So did you catch it? So this is a technique that, so if this would be like if your sequence is like a polynomial, similar to a polynomial function, and you might not know that, but you just kind of give it a try. So you start writing down the variations between two terms and continue that pattern until you can find maybe there's a linear pattern will emerge, and then you can work backwards to figure out to what degree polynomial your sequence is. And then that can help you. So we figured out it was cubic, so we wrote the sequence of I cubes, and with the sequence of I cubes, we could see what the pattern was. Any questions on that? Okay, so we want to talk now, talk about something called convergence of sequences in series. So convergence and divergence of sequences in series. Okay, So an infinite sequence converges if all the terms after some place in the sequence become essentially indistinguishable from each other. Okay? So if you get far enough down, far enough into the sequence, the terms are essentially staying the same. Like it's honing in on the sequence hones in on a particular value, and technically always gets closer and closer and closer to that value. Never stops getting closer to that value. But then you get so close that for practical purposes, you just essentially say, it's just that number, then forever. Okay? So this is the idea of a limit. So in other words, a limit of a sequence that converges is a finite value. So this is our limit notation. Here's our sequence in function notation. This is saying, look at, as I goes to infinity, look at what this sequence of terms does. If it does this, if it gets essentially, infinitely close to a particular number and always getting closer and closer, then we call that number the limit, L, the limit of the sequence. If it does not hone in on one value, if it does not keep getting closer and closer, always closer and closer to one particular value, any other situation, we call the sequence, we say that sequence diverges. Okay, here's an example. So the very first one we did, 1, 3, 5, 7 is the odd numbers. This is our 2i minus 1, right? 2i minus 1 is the very first one we did. Does this converge or diverge?
Diverge.
Diverges, right? It's just going to keep going up and up and up. There's no limit to how big the numbers get, right? And that does not fit the bill of honing in on a particular value. So this was the second one we did. We came up with, so we had this alternating sequence, and we came up with the formula negative 1 to the I, 2i plus 1 over I plus 1 squared. Okay, so what about this? Well, what are these terms doing? Well, this problem is like a pre-calc problem when you were doing rational functions. So this is analogous to a rational function. And in pre-calc, you studied rational functions, and you looked at the end behavior. Or this is like horizontal asymptote. And how do we do that? So this is similar to, say, and the fact that it alternates doesn't make a difference for, well, it might. So we'll just talk about the alternating effect at the end. But this is essentially 2x plus 1 over So what happens here? So this was when we were analyzing our rational functions, one polynomial divided by another, and we just saw that with the in the partial fractions. We know the rational function is one polynomial divided by another, and so to know what's going to happen at the ends of a rational function, we look at compare the degrees. Here, the numerator has a lesser degree than the denominator. And if the numerator has a degree less than the denominator, do you remember what happens here? So this will get much, much, much bigger than this. In fact, say when you get to 1,000,000, this will have 1,000,000 squared, and this will only have 1,000,000. And when you get to 1,000,000,000, the denominator will have 1,000,000,000 squared, and the numerator will only have 1,000,000,000. So if the degree of the denominator is greater, and you think about x getting to be very, very large, well, it's going to be at least that factor, whatever x is, and x will keep getting bigger and bigger. You'll have an extra x. So like I said, if it's a quadrillion, then this will be at least a quadrillion times as much as this, because you have x squared here and you have x here. So what will f of x do as x gets big?
Approach.
Get closer to 0.
0, right? If the denominator gets much, much bigger than the numerator, then that if it just keeps getting infinitely bigger and bigger in the denominator compared to the numerator, then that will go to 0. So if this is going to 0 and it alternates, that the alternating won't make a difference if these terms are getting closer and closer to 0. Now, if these terms are getting closer and closer to, say, 3, say we're getting closer and closer to 3, and then it was alternating, then that would diverge, because in the end it would be like 3, -3, 3, -3, 3, -3. But an alternating effect on values getting closer and closer to 0 doesn't mean anything for us. It'll still converge to 0. So this converges to 0 as I gets very big. Does that make sense? Any questions on that? All right, here's this last one. How about this? 2 to the I minus 1 over I. Let's look at the terms. So 16 fifths, 16 thirds, 64 sevenths. So 2 to the I minus 1 over I. So some of these, it's just kind of a reasoning thing. So let's think about when I gets to be 100, we'd have, I was trying to, wow. Trying to get my pen. So we could try, say, when I is 100, we'll have 2 to the 99 over 100. And if I is 1,000, we'll have 2 to the 999 over 1,000. What do you see happening here? What about 2 to the 999th power? Is that bigger or smaller than 1,000?
Way bigger.
Way bigger, right? Multiplying 2 together like almost 1,000 times is going to be way bigger than just the number 1,000. So this numerator is just exploding, right, compared to I getting bigger. So this is diverges because these numbers just get huge. Okay, so that's just some basic examples. So let's look at some common forms of sequences. First is a p-sequence. A p-sequence has this form. 1 over I to the p. So where p is a fixed value, p is a constant. So we're going to ask, for what values of p does I to the p get really big, and thus the reciprocal get really small? So for what values of p will this just get large without limit, right? Large without bound. And if it does that, then this whole thing will converge to 0. So when you see this, what do we think? So see this, think what? What do you think when you see this right here? Super important question.
It's going to converge at 0.
Nope, I'm not asking about convergence or divergence. I'm asking when you see this notation right here, what do you think? What does it mean? What is it? What's that?
A list?
A list. It's a list, right? So see that? You think, oh, this is a list of numbers. Let's write them out. What's the first number in the list?
1.
1. Second number in the list?
1/8.
Good, 1/8. 1 over 2 cubed. Then 1 over 3 cubed.
1/8. Okay.
1 over 4 cubed. So make sure as soon as you see something like that, you think, oh, that's a list of numbers, and I know I can generate that list by letting I be 1, and then let I be 2, and then let I be 3, I be 4, etc. All right, what about this? So then the gentleman who answered originally, now let's talk about convergence or divergence. Will these denominators does the denominator get large without limit? That's the question. Does the denominator just keep getting bigger and bigger?
Yes.
Yes. Yes. Therefore, the reciprocal gets smaller and smaller, and this will converge to 0. So, converges. How about this? What list is this? 1. So this is square root, right? 1 over square root of 2. 1 over square root of 3. 1 over square root of 4, or 1/2. What about 1 over the square roots? Does the sequence of square roots get really, really big and keep it getting bigger and bigger? Do square roots get larger and larger? This is the square root function. Or does this level off? Square root of x.
It levels off.
So I have a vote for levels off. Square root of x. So the square root of a million, the square root of a billion, is that bigger than the square root of a million? And then the square root of a trillion, is that bigger than the square root of a billion?
Yes.
Yeah, so these will get as big as you want, right? So you can get any number, right? You can get any number in this sequence that you want just by, so if you want to get a quadrillion, just put in x is a quadrillion squared, and this will be a quadrillion. If you want to get a Google, right, 10 to the 100th, right? If you want to get a Google, just put in x equals a Google squared, and this square root of that will get to a Google. So there's no limit on how big this gets. It just gets big much slower than, say, I cubed. So it gets big more slowly, but it gets as big as you want. So this converges. What about this one? What's this list? This is 1, but then what is essentially 1 over I to the negative 2 is the same as?
I squared.
I squared in the numerator, right? Is this going to converge?
It would diverge.
Diverges badly, right? You just keep squaring, 1 squared, 2 squared, 3 squared. This just gets really big, right? So when does a p sequence converge to 0? Converges to 0 as long as your exponent, I to the exponent, is positive. All it needs to be is positive. Now this is not a proof, but we're just thinking about it and showing some examples, but it's not a proof. As long as p is greater than 0, as long as your exponent in the denominator is positive, the denominator will eventually get as big as you want it to get, and therefore the terms of the sequence will approach 0. Okay, one more thing to just mention, and then we'll take the quiz. Questions on p sequence. So remember, a p sequence is when you take your 1 over your index raised to a constant power, which we call p. So cube stays the same in the whole thing. 1/2 stays the same. Your index is your base. Your index is your base. In contrast to that, a geometric sequence has this form. Your constant is in the base, and your index is your power. So let's, for instance, 2 to the I. That's a geometric sequence. 2, 4, 8, 16. Powers of 2, right? It's a sequence of powers of 2. So your index is now the exponent. That's geometric. Geometric index is the exponent. P sequence, 1 over I to the p. Your index is your base in the denominator. See the difference? Okay, so we'll start by analyzing geometric sequences next time. But this is on the quiz, so just want to make sure you got it. That for geometric sequence, the index is the exponent, and your base is constant. For a p sequence, it's 1 over, the index is the base, and your exponent is constant. 1 over I cubed, or 1 over I to the 1/3, something like that.